Okay, so let's remember what we were talking about. We are going to finish the concept of cache, okay? And we will make an example of how this would affect your writing of programs to which would have much better temporal and spatial locality. Okay, but before I go on, let's remember that what we talk about the cache is it's essentially a faster but smaller memory that's close to your CPU. Okay, this is what I mean. And we usually have a lot larger but slower memory element below this. And basically, what we do in between is what we call caching. Okay, the issue is, I have so much data in here, and which of these data should be basically brought into the cache for faster access, and how should I handle that? Okay, that's the idea. So with the cache, we said that there are three parameters that specifies the cache, and one of them is the block data block size. Okay, and this means that whenever you cache something, you cache a whole block of them. Okay, I mean if you only need say 1 byte from this, it's the example was that it's if you need only one line from a page, you have to take the full page from the photocopier. Okay, and there's the number of lines per set, which is set as E here. Okay, and the number of sets, and the cache size is specified as the total number of data bytes stored in the cache. And the way it worked was as follows. Remember that in from the CPU point of view, we're given an address, right? And this address, okay, so that like we have that many bits, okay. And we know that, like, if say, imagine that for the lower level, this address is sufficient. But for the upper level, well, you have much fewer places. Okay. So how are you going to then, use this address to see whether the data that you're looking for is actually in the cache or not? Okay. And that's first thing. And then, and then how are we going to then, if it's not in there, then we have to bring it in. Okay, so the address is split into three parts. The first part we split as block offset. Okay, this is actually determined by the data block size. If b the data block size is as 2 to the power b, then it means that I have to set b bits here, okay, as the block offset. Well, this is pretty obvious. And then we said that we will then use other bits here as the set index. Okay, and the set index again, if the number of sets is to power say s, okay, then we will be using s bits for this. Okay, and then the remaining part of the address, we call this as a tag. And when we cache a data in our we need to store, like, we have this structure that's called a line. And in the line, we obviously have this data block, and which has a size of b bytes. Okay, and along with this data block, then we also store the tag. Okay, and along with the tag, then we also store this valid bit. Okay, and the way it works is as follows. So we said that with each of these lines, then we have the concept of a set. Okay, a set is essentially kind of something that's puts multiple lines into a group such that checking basically checking whether the data that you're looking for is in there or not. And in our examples, if you remember, we were talking about that we are all getting these different photocopies, okay, as we need to cache them in. But when you have too many photocopies, then it's difficult to see whether the page that you're looking for is among them. So the one way to do this is you do a search. You compare the tag in your address with the tag in the cache blocks, okay, and then to see if there's a match. But this is like, this is too much, okay. And if you want to split this, if you want to reduce this, compare the number of comparisons, one way to do this, you can group them into basically multiple kind of like folders. For example, you can put your odd number of the pages with odd numbers into one folder, and the pages with even into another folder. Okay, so then when you get an address, then you can use by looking at the address, you can say if this page is in the cache, then this should be in the even folder. Then you can just compare, only make half the comparisons to do that. So what we call as a set is essentially we have this set in here, and in the set then we have a number of basically lines. Okay. And with this, then we said that we could that there are the different types of caches. Okay, and for cache, so we said that the types of the caches are determined by what we call E. Okay, and E is essentially the number of lines in a set. Okay, in the cache. So when E equals 1, okay, which is we have put a different name. We say that this is a direct mapped cache. Okay, and in this case, what we do is we have these sets, and in each, like whatever sets that we have, and in each set we have only one line. So this can be, for example, this is like say odd and like take our case with odd and even. In this case, in each folder, I can have only one page stored in that. Okay, so if if I, for example, so have 10, like in the case of decimal numbers, if I just have 10 sets, okay, that means that I have basically 10 folders. By looking to see the last digit of the page, then I can say that, well, if it's 0, then it should be in this folder, and there's only one page in there. If it's 1, it should be in here. So this is basically in the direct mapped cache. And what you do is, whenever you are given an address, you check whether the tag here is the same as one. You make basically one tag comparison, okay, per access. If it's in there, then then it will find. If it's not there, then it will be a cache miss. Okay, and with this, then there's we can get this with like what if E equals say K. Okay, we call this like E equals K, and this we know, and we say that this is a K-way set associative. In the case of basically K-way set associative, we say that this set has K lines in it. K lines. And this means that you have basically K tag comparisons per access. And with this, then you can say that if you go all the other way, if we say that, if we set S equals S1, which means you just have one set. Okay, it's like you have You put everything in that. This is the case where basically E, okay, it's difficult to say basically what E is because it depends on how many sets, how many lines you have. Okay, so E equals number, well, say that total number of lines in the set, so in the cache. This is important. Okay. And in this case, in the following case, remember that I still have multiple sets. Okay, each of which are basically having this K. Okay. In this case, which we mark as, and this is important, this is called a fully associative cache. Okay. In this case, we say that everything is one set. Okay, there's no other set, and we put all the basically lines in this case, in this one. Okay, this is basically what we call a fully associative cache. And in here, you can see that, like, when we compare the fully associative cache and the direct map cache, in the direct map cache, it is comparisons are much less. You just have one tag comparisons, and whereas in the case of fully associative cache, then you have basically you have to make many comparisons. Like you have to make okay, comparisons, tag comparisons. Okay. Okay, there's a question. Let's see that. Okay, John, can you explain what's the trade-off between S and E? Is higher S or higher E preferred? Well, S and E, they are kind of like S and E is S is this like let me say, with S and E it works as such. Okay, so given given a cache size, okay, which is C, okay. Remember, C was equals to, say S times E times B, okay. Now let's say that B is fixed, okay, and if you and of course, like we said, that if our cache size is also fixed, then S times E should be the same, right? And in this case, like say if it means that S times E, this gives you basically when you multiply the number of sets times the number of lines per set, this tells you the number of lines, okay, number of this total lines in the cache, okay. And the way, depending on your set, like let me do this with an example. For example, imagine that this is my table, okay, and I can, on one hand, I can have 4 pages or 4 lines. Okay, it's 1, 2, 3, 4. Okay, and if I have no set, which is actually the simplest case, then you have to make you can put basically 4 lines here. Then you have to make these tag comparisons, 4 tag comparisons in here. This is kind of like the fully associated. Okay. In the case of direct map cache, then we also put them into these basically sets, and let me say in this fully associative cache. Okay, this is a full set. This is your set. But effectively, it means that it doesn't make any sense. In the case of direct map cache, then you have 4 sets, and in this case, you have 1 line per set. And if I have like, two-way set associative, then it's like this. You have two sets, okay, set 0 and set 1, and in each of them we have two lines. So you can see, like in here, that for example, if I take my the set index in here, in this case, any page can go into any place, and in here, depending on, for example, imagine like this is my, like I can say that this is set 0, 0, okay, this is set 0, 1, and this is set 1, 0, and this is set 1, 1, okay. In here I have two sets. It's set 0, okay, and set 1, okay. In this case, well, you don't have anything. So what you do is, in the address case, like given an address, memory address, okay, then in the fully associative cache, well, you have the block offset, okay, and you don't have any set index, okay, so you put your tag is the rest, and this is where your tag is, okay. In the case of direct map cache, again we have the block offset, okay, it's the same because we have the same. But then in here, then in this particular case, then how many sets do I have? I have 4 sets. It means that I need to have a set index, and this will be 2 bits, okay? And the rest will be the tag. But in the two-way set associative, and again the address, here's my block offset. Then in here I have 2 sets. So it means that for my set index, I use 1 bit, and then the rest I use as my tag. Okay? So in here, the cache size is the same. Cache size is basically blocks, number of blocks times 4, right? The block size times 4. And when we look at here, now which one is better? You're asking me. The fully set associative is actually the best thing, because in the fully associative one, then you can put, if you have a new data block, you can put it into any place, any of the lines. So you have a complete freedom, okay? And but the comparisons, so if you go to it here, then the more, let's see that, maximum number of comparisons, of tag comparisons needed, okay? In the case of direct map cache, I only need 1 tag comparison. And in here, I only have to make 2 tag comparisons, okay? Now, what's the downside with the direct map cache? In the direct map cache, you can have too much collisions, meaning that, depending on this set index, okay, certain pages have to compete for the same set. I mean, for example, let me just think about, the 2 addresses. For example, I have an address, just for the tag, I'm saying that 2 examples, let me put them with the screen, okay. So let's look at these 2 addresses. In this case, if I have like 0, let me see, 1, 0, and then, say for the block offset, maybe I say 1, 1, okay? So this is the set index, if I assume that, okay? And then if I have another memory element, which is, say, 1, 1, 0, 0, 0, okay? You can see that, they look very different. And imagine that with this one, I had a miss, and you bring this into your direct map cache. And where do you put this? You would put the data for this address into 1, 0, into here. Okay? So you put this in here. Now, after that, imagine I am accessing this second one. And note that the other three sets are empty. Now after this, if I now access the second line, and after this, now if I access this one, note that it also has the same set index. So where do you put it? Well, this was a miss, okay, and then you put it in here. Then you can see that it will again be a miss, and then you have to write this one. It will again be a miss, but then you have to write this again onto here, okay, overwrite it, despite the fact that the other three are still empty, okay, because of this. Now, what happens in a full associative cache? In the full associative cache, again, this again, 0, 1, 0, 1, 1, and then 1, 1, 0, 0, 0. Okay, so if it's like 1, 1, 0, 0, 0. Okay. Now, in the first one, when I have this basically thing, it will be a miss. Okay, and then you will put this into one of these lines. Which one? Anything would be okay. Maybe I will put it here. Okay. Okay. So you put it here, and then comes the second one. Okay. And when second one comes, well, this one is one, but we have three others empty. And in this case, then you can put the second one into here because you have that flexibility. Okay, you can see that in the fully associative cache is actually much better in here. Now, what's the downside? The downside is whenever you are accessing the cache, you need to make 4 comparisons at any time. Okay, so that's the price that you pay. And in the case of this two-way set associative, okay, in this case, let me see for the first one, okay, where's the set index? The set index that we use is this one. So this is my set index, okay? And given this, what I do is, since I have, like when I try to do this, then you copy this into one of these lines. So it has to go into set 0, okay? So you put in one of them. You can have put it here or here. So let's put this green one in here, okay? And then comes the next one. Note that this also has the same set index, okay? And this was like, this was the same problem that we had in the direct map cache, which caused a collision here. But in here, since I have more flexible, then now you can put this new one in here, okay? Of course, like if I have a third one, okay? If you have a third one, maybe let me see that. If I have a 1, let me see, 0, 0, say 1, 0, okay? If you have a third one, then you will have a collision, okay? That will lead to a collision, okay? And in here, then you will have, let me delete this here, okay? And in here, then you will have this collision, which will result in the deletion of this one. And you will put it here. In here, you will eventually have a collision, but this will happen at a later time. Okay. So more comparisons in full associative cache, yes, because like you're more flexible. You can put a line in any of the empty slots. Whereas in the case, but when you're finding, then you have to make all these comparisons. Because in the direct map cache, there's only one place where a page can go, but that's easy to search for. But on the other side, you may have more collisions of this. Okay.